Great. Okay, so today I'm going to talk to you guys about, first of all, my name is Jane Fowler. I'm an assistant professor in environmental microbiology at Fraser University in Metro Vancouver. And I'm going to talk to you guys today about a group that I've been working with for the last 4 years called the Cold High Anaerobic Digestion Group. We call it CHAD for short. And this group is focusing on developing psychrophilic anaerobic digestion technologies to improve sanitation and to some extent, energy security in the rural and remote Arctic. And so I just wanted to start out with a land acknowledgement. So where I work and where I live as well, and where I'm speaking to you from today, is on the unceded traditional territories of the Coast Salish peoples, particularly the Squamish, Musqueam, and Tsleil-Waututh nations. A lot of what I'm going to be telling you about today is about Alaska. And so I just wanted to show you this map of Alaska that shows the different tribal groups that are present in Alaska, the major tribal groups and the language groups. And so currently in Alaska, there are 228 federally recognized tribes, and there's probably a few more that are unrecognized at the moment. And when we're thinking about developing and improving sanitation technologies for these kinds of groups, I think it's really important, and this is something that was emphasized to me at this conference I was at a couple weeks by an Alaskan native named Robbie, that we use two wide-seeing approaches. So by taking both Indigenous knowledge and Western knowledge and co-creating systems to ensure that they will be more sustainable, both in terms of their environmental impacts, but also as something that will work for the communities in the longer term and not just, end up being something that's more of a burden for them than a benefit. All right, so when we think about anaerobic digestion, a lot of us probably think of systems like this, really large scale systems that are used in places like wastewater treatment plants. But smaller scale anaerobic digestion can also be used as well. And so essentially anaerobic digestion is just a biological process that converts all kinds of different wastes into biogas, which consists of CO2 and methane. This can be used then as an energy resource for fueling all kinds of things. We have these large scale installations for treating wastewater sludge, as well as food waste, agricultural waste, and so on. But most of the anaerobic digestion installations that exist, they run at mesophilic and thermophilic temperatures. We do not know a lot about psychrophilic anaerobic digestion, and not a lot of work has been done. But although these would benefit, people living potentially in remote locations in the Arctic, it could also benefit a lot of these mesophilic and thermophilic installations in the temperate regions of the world, because a lot of energy has to go into heating these systems up to maintain the temperatures. And so I'll just give you a bit of a technical overview of the biology that happens in the anaerobic digestion process. And so this might be the most technical slide in the talk, so don't worry about it if this is going over your head. So essentially the whole idea is that anaerobic digestion starts with these large polymers like proteins, carbohydrates, and fats. Those get hydrolyzed by what we call hydrolytic microbes. They convert these polymers into smaller molecules, things like amino acids, monosaccharides, fatty acids. Then these smaller molecules get fermented by fermentative microbes, which we often call syntrophs, and they produce things like volatile fatty acids, acetate, hydrogen gas, and CO2. And then these more simple compounds are converted by a group of organisms called methanogens that convert hydrogen, CO2, acetate, and a few other C1 compounds into the final product, which is methane, and as well as CO2. And so there's a lot of different groups of microbes that carry this process out, and the interactions between these microbes really impact the effectiveness of the process and the feasibility of these reactions to actually occur. Now, when it comes to psychrophilic anaerobic digestion, there's a few challenges that exist compared to these mesophilic and thermophilic systems which operate at higher temperature. So psychrophilic, I don't think I described what this means. Psychrophilic just means low temperature. And so typically I think of psychrophilic anaerobic digestion as something occurring below 20 degrees, maybe even below 15 degrees. And so at these low temperatures, the diffusion rates are slow, and some of the substrates like lipids are going to be solid because it's below their melting temperature, which means that their bioavailability is low. In all anaerobic digestion technologies, hydrolysis tends to be the rate limiting step, but this is especially so in psychrophilic systems, where especially lipolysis is a rate limiting step. We have I think there's one paper out there that talks about anaerobic digestion microbial communities recovering from freeze thaw. So for example, if you're in the Arctic, right, your system might freeze for a certain period of the year. And the question was whether these systems could actually recover and become active again after thawing. And there is some sort of lab scale experiments that have been done that suggest that this is possible, but a lot more research needs to be done on that. But something that does seem to be important is using cold adapted inocula to start these systems up. So you want to find a microbial community that comes from a cold environment. Whereas a lot of people, what they have done is they've taken communities from mesophilic or thermophilic anaerobic digestion systems and just put them at a lower temperature. And this doesn't tend to work well. And this is probably because there are special microbes called psychrophiles, which are adapted specially to work at these low temperatures. And so you really need to have these psychrophilic organisms that are adapted to those conditions in order to have the best anaerobic digestion performance. And so overall in this area, very little research has been done. I did a literature review on this topic for this conference that I'm going to tell you about. And I found really it wasn't a lot of work because there just isn't a lot of papers out there. So I think that in terms of the research opportunities there, it's probably more opportunities than challenges, although there's also a lot of challenges. All right, so as I said, most of this talk is actually going to be an ad for a group that I've been working with for the past 4 years. And so this is the Cold and High Altitude Anaerobic Digestion Group, or CHAD. And so the US EPA, in their responsibility to the Alaskan Tribal Trust, started discussions with Washington State University back in 2019 to 2020 about the potential of using AD, anaerobic digestion, as a means of improving sanitation in the remote Alaskan native villages. And so this led to the development of the CHAD groups, which was started by Margaret Macaulay at the US EPA, as well as Embry Ronstadt, who at the time was at the Washington State University. And so the group quickly grew to be very diverse, including a number of academics, people that work in different government agencies, people working in industry, so all kinds of different industry, like in consulting and other areas, engineering, scientists, engineer policymakers, all kinds of people. And then it also kind of grew beyond just people that were interested in the Arctic into people who were interested in high altitude as well. So there's a number of places in the world where anaerobic digestion is actually used at high altitude, and these include the Andes. So there's several people involved in the group from Colombia and Ecuador who work in the Andes. And then there's also at Mount Everest Base Camp, there is an anaerobic digestion installation started by the Mount Everest Biogas Project. And so they're also, people from that group are also involved in CHAD. And so we have monthly Zoom meetings, one Wednesday a month at 9 a.m. Pacific time. And if you want to find us or join the group, I recommend going to our page on the IARPIC collaborations website, which I'll give you the link for later, or you can just search IARPIC collaborations. And so I said we've been talking since 2020, online monthly meetings. And so finally, about 2 weeks ago, we had our first meeting in person for the group. And for this, I really need to credit one of the group members, Robin Schmidt, who wrote a grant to NATO, actually, that allowed us to actually hold this conference. And so this was a couple weeks ago in Fairbanks at the National Renewable Energy Lab's Cold Climate Housing Research Center. And there were people from many different countries that were able to attend. And this is a group of most of us at the US Army Corps of Engineers permafrost tunnel, which we had the opportunity to visit while we were there. And I have to say, in terms of the experience at the conference, I haven't been to many conferences that had this high quality of discussion. There's an extremely high level of inclusion. And I think that this is partly due to, well, all the wonderful people involved, but also the diversity of experience that we have. And so there's kind of no stupid questions because, you know, a policymaker might not know something technical about AD, while I don't know anything about or very much about policy. Although I have to say I know more now than I did 2 weeks ago. There was a huge range of participants, and this really elevated the discussion of all of the topics. And everybody was super open-minded and really interested in learning and finding solutions. So one of the things that we talked about at the conference, so the Cold Climate Housing Research Center is going to be hosting a pilot anaerobic digester. And so this digester is being funded by the US EPA. And so we're currently working on developing a design for this, identifying where we should get the seed inocula from, thinking about how we can extend the active period of the digester by using things like solar power, that kind of thing. And we also are interested in understanding how the digester will recover from freezing. And so one of the afternoons of the conference, we also talked about what are we going to feed it. So the Cold Climate Housing Research Center doesn't have any biohazard permits, so we are going to have to feed it synthetic feces. So we worked on making some synthetic feces, and you can see from the pictures that some people got really artistic, and we all had a lot of fun making fake poop together. This is a bonding experience if you didn't know. So I can recommend it for your lab groups. All right, so I'm going to now talk a little bit about the situation in Alaska and the challenges that are being faced and the solutions that we're trying to solve, or that we think we might be able to solve. So Alaska is a very large state. It has less than 1 million people, however, and so the population density is really low. And so you can see from this map that there are some highly dense areas around Fairbanks here and Anchorage down here. And a lot of the rest of the state is really sparsely populated. So somewhere between 0 and 1 people per square mile over most of the area of the state. The median household income in Alaska is $86,000 US per year. And 11% of that population live in poverty. The people living in these remote villages, their household incomes tend to be a lot lower than the median. Alaska also has the highest percentage of indigenous population in the US. I think it's around close to 20% of the residents of Alaska are Alaskan natives. And so in these really sparsely populated regions, most of the communities that are there are not connected to the road system. And so you can see there's about 250 remote villages, and you can see a lot of them labeled here. The villages along the coast here and along here, they're mostly not connected to any road system. What that means is that for most of the year, most of the goods are brought in by plane. During the summertime, there's a couple of barge services every summer that will provide additional supplies. Sometimes there can be some travel between closely linked communities by, for example, snowmobile or quads and that kind of thing. But really, they're getting most of their supplies by plane, and then in the summer by barge. So very remote and difficult to access and expensive to access. And, so the price of goods in these places are very high. And so that creates a lot of challenges to sanitation services there. So the costs, as well as the logistics of building systems in these remote villages, are very complicated and high. So it's expensive to get anything up there. It's expensive to get people up there, as well as the actual building supplies as well. The logistics, getting these larger supplies up there are also a bit complicated. The other problem is that piped systems for drinking water and wastewater, they don't do well in Arctic conditions. So for example, like here, I think this is I can't remember which community this is, but you can see there's above ground piping here. That's because it's likely permafrost underground. So they build these systems above ground, but with the freezing and thawing, these systems really don't last very well in the conditions. And so what that means is that the operations and maintenance costs are extremely high. And so while infrastructure funds are often available from the government to actually build these systems, which means that often they get these highly technical systems dropped in on them that are expensive, and then they aren't feasible to maintain at reasonable costs for the residents. So the residents typically end up paying those costs for operations and maintenance, which creates a lot of issues for them, because then a large proportion of their income actually goes to operations and maintenance of these systems. And so as I'm going through these next few slides, I just wanted to point out that a lot of this information is coming from, and the images are coming from the Alaska Department of Environmental Conservation, but especially from Simone Sabalo, who is a consultant at the Zendra Environmental Group, who shared a lot of these images and information with me. So what does sanitation look like in these remote communities in Alaska? So there's a couple of different scenarios. So first I'll talk about the served communities. And the served communities are those that have greater than 55% of the homes that have piped systems or have septic tank and wells, or what we call a covered hall system. And so you can see the number of communities that have these different types of systems out of around the 250 remote villages that I mentioned. And so especially these covered hall and pipe systems have extremely high operations and maintenance costs. Someone from the Alaska Department of Environmental Conservation was talking about on the order of around $500 per month for some of these residents to pay for these systems. And so you can imagine, if you are low income, you're really thinking like, why would I spend that kind of money when I need to also buy food for my family, right? So these exorbitant costs really limit how useful the sanitation systems actually are to the residents. And so I just wanted to show you guys, so the covered hall systems, which I was not familiar with before. So these two pictures show what a hall system is. So typically there's a area outside the home here where sewage and gray water will accumulate, and then someone comes in, pumps those systems out, and that will then get dumped into typically a sewage lagoon or a landfill close to the communities. So those are the served communities. The other scenario is unserved communities. And so unserved communities are those where 45% or more of the homes are not served by a pipe, septic tank and wall, or covered hall system. Currently in Alaska, it's estimated there's about 32 unserved communities. These are mainly in Western Alaska and along the Yukon River. So you can see them highlighted in red in this picture. And the populations in these communities range from about 50 people to up to 700 people. So that's a huge community that's completely unserved. And as I mentioned, so the median household incomes in these communities tend to be a lot lower than that of the entire state. And so in these unserved communities, obviously there's no options to use sanitation, but even in these served communities, there's still a lot of people that would be considered unserved, either because their homes are more remote and can't be connected to the system, or because they just can't afford to pay the operations and maintenance costs. And so they just become an unserved household. And so what does it mean to be an unserved household? So when you're an unserved household, typically what you use is a honey bucket system. And so a honey bucket is basically just a plastic bucket that's lined with a plastic bag. There is a region in the house where this would be located, and you use it for urine and feces. There's also going to be toilet paper in there. Typically, people dump a lot of Pine Sol in there to deal with some of the odor issues. And other things get thrown in there too, like cigarette butts, small toys, garbage, and all kinds of flushable and non-flushable wipes. So once these honey buckets are full, then they are tied up, which you can see down here, and disposed of. There's a few different ways they can be disposed of. Some communities have what are called hoppers, which is what you see in this image here, where they just dump the honey buckets in there. They're collected in the communities and then eventually disposed of into lagoons or landfills. A lot of the time, these hoppers will leak. And a lot of the time you can see kids are sometimes involved in dumping these things, which is a bit worrisome. This is another example. Sometimes they might just be like a ATV that goes around and collects the honey buckets at certain times, and then they'll just go and dump them into a landfill or a lagoon or elsewhere in the environment. So in general, the use of honey buckets is, well, there's several concerns in terms of public health and as well as dignity. It just doesn't seem like a nice way to live. And so I just want to show you guys this video. This video is made by some teenagers that live in Chifornak, which is a coastal town of about 500 people in the Yukon Delta. And this is a video they wrote about honey buckets.
Me and my friends, we're gonna dump honey buckets from my house onto the dump. It's gonna be a whole lot of fun, and it's gonna be dirty. Oh no, gonna dump honey buckets into the lagoon. Probably some trash to my house. Yeah.
All right, so that's people I don't think really want to interact with the honey buckets. Definitely teenagers cleaning them up is maybe not the most fun thing to do with your weekend. So I just wanted to look at where there's kind of issues in this whole system that would be useful to solve by some kind of improved sanitation system. So firstly, when you're using the honey buckets in the home, there's the potential for exposure to human waste. And of course, there's the odors that are in the home that would be good to solve. During the transfer of these honey buckets from the home into the hoppers or into the lagoon, wherever they go, there's another opportunity for exposure to human waste. A lot of the time, the kids want to be involved in this process. It's like excitement going on, and this is really not a great thing for kids to be exposed to. And then lastly, there's these environmental and public health issues related to the disposal. So you can see here, this lagoon, there's a lot of plastic bags accumulating in the environment. It also results in the exposure of animals and birds to all of this waste as well in the environment. And there's also problems with environmental degradation related to these untreated waste sitting in landfills or lagoons. And this is especially important in these villages where people rely on shallow sources or surface sources of fresh water for their drinking water. This is especially important in the permafrost zones where there's really good ability to drill down and get groundwater. And they also rely on a lot of local food sources, like fish and other animals that are collected from the environment that could be exposed to these wastes as well. And so one thing we discussed at this conference was how would these AD systems actually help? And we realized that actually we're not really solving many of these problems. The main one that we would be able to work on would be the environmental and public health issues related to disposal. These other issues with regards to people being exposed to waste and odors in their home, and also during the transfer of the honey buckets in these unpiped communities, they still exist and they still need to be solved, even if we get psychrophilic anaerobic digestion systems working perfectly, which in itself is a major, question mark still. Another issue that exists is the social barriers. So this is, I'm just going to highlight some of the things that a woman who was at the conference, Jasmine Perea. Jasmine is an Alaskan Native. She just completed her bachelor's degree and she's now working for the Zender Environmental Consulting Group. And she talked a lot about the social barriers that exist to getting these communities on board with implementing these technologies. So there's a barrier to using human waste as an energy resource. So using that biogas that comes from human waste, people, of course, think that that's a bit questionable. And there's also social barriers to actually implementing technical systems that won't break down. So a lot of these communities have had bad experiences in the past where, people have come in, dropped in this really highly technical sanitation system that's going to make their lives so much better that eventually they just break down. They can't be fixed because they're not made with local materials or there's no local expertise in the communities to fix them. And so they end up just being, a pile of garbage that's present in the community that they can't really do anything about. And so Jasmine thinks that the solution to, one of the solutions to dealing with these social barriers is to use pilot anaerobic digesters as a way to get communities involved in the process of anaerobic digestion, understanding what it is. And she proposes to not only use human feces. And so the feedstock that she is interested in is dog poop. And so in Alaska, there's around 65,000 dogs that together create about 24 tons of feces every day. So this is a huge source of feedstock that could be used for anaerobic digestion. Well, I'll tell you a little bit about what Jasmine has done. Another thing that we really need in order to help break down these social barriers are champions in the communities that are really committed to the long-term system functioning of these systems in the community. So if we can get people who are in the community excited about these things, get them to learn how they work, make sure that they're being maintained and in a way that's going to allow for long-term functioning, make sure that there are some simple ways to fix them, then this will go a long way to improving the longevity of those systems and improving the long-term benefits of these to the communities. So Jasmine, as part of her capstone project in her bachelor's degree, decided that she wanted to start an anaerobic digestion system. And so she set it up in the greenhouse of the university farm, which you can see here. And she started running it with dog poo. And so this is something that's typically not recommended. It's said that dog poo has too much protein in it to actually have well-functioning anaerobic digestion, but obviously it worked fine for Jasmine. And so what she did is she took a commercial system that's called the Home Biogas 2, and she just purchased it. And then she insulated the system really well using insulated pads underneath of it and around it. And she heated the system with seedling mats and an aquarium heating probe. And all of this allowed her to run this system at around 80 to 90 degrees Fahrenheit throughout the entire year. So it was able to stay warm even in this unheated greenhouse. And so when she started up this digester, she needed to, and when she feeds it, she makes a slurry of dog poop mixed with water, 1-to-1. She started out with 100 liters of dog poop to do the startup, and then she feeds it around 30 liters of dog poop every day. This runs a gas stove for about 2 to 3 hours a day. And so she was often taking frozen dog poop. It's recommended to use fresh organic matter, but I mean, obviously the practicalities of that in somewhere like the Arctic are not really feasible. So she was often mixing frozen dog poop with hot water to create this slurry. And so this is just a video she sent me about making the slurry. And so you can see her making the slurry. She uses a paint mixer and a drill to get the consistency, to get a well mixed consistency. And then you can see her feeding the digester at the end of it. And so Jasmine was also able to eventually use the biogas that was produced by the system for running a burner. So she's able to run it for about 2 to 3 hours per day based on daily feeds of about 30 liters. And this is another video.
It is April 17th. I made my first 3 eggs on my home biogas 2, and now I'm going to eat it.
And so I think that that's one good example of how we can use small scale AD as kind of a illustration of what is possible. And Jasmine was able to show that you can even use dog poop, even though, you know, this is typically not thought to be possible, but it was totally effective and it's running really well and really efficiently. Another example of cold and small scale anaerobic digestion systems that actually work. So these are some tubular anaerobic digesters that are within an insulated solar collector. These are located at a climber or hiker refuge in the Andes in Bolivia. For people that are climbing this mountain, Huayna Potosi, I don't know how to say that. Sorry if I killed the pronunciation. But so this refuge is at over 5,000 meters, and these tubular digesters are used to treat the waste and gray water that are produced at this refuge. So this was set up by Jaime Martí-Herrero, who works at IKEM University in Ecuador, and he also works with a couple of people that were at the conference from Colombia as well, Liliana Castro and Jaime Esteves, who have set up a number of these kind of tubular digester systems in the Andes at farms and different locations. Another example, so there was another woman, Angie Bywater, at the conference who actually runs her own backyard digester. She's been running it for several years now. This is a 200-liter system that runs from about 15 to 40 degrees. She heats it with solar power and also mixes it with solar power. And it's fed food and garden waste. And so she takes the digestate from the system and puts it on her garden. As you can see, produces all kinds of beautiful vegetables with the digestate from from this digester, and is also able to produce biogas that can be used for, she uses it for different things like heating greenhouses or cooking on her biogas stove and that kind of thing. So in general, I think these are good examples that say that cold and small scale anaerobic digestion systems do work. They require somebody who's really invested in getting them to work. And of course, the examples I've given you, maybe they aren't the same as working in a remote Alaskan village. And so there's a lot of challenges that need to be addressed there, both in the operations, but also the design and how do we get these systems to these villages. We're talking about flat pack design and using local materials, or at least materials that are available locally, so that maintenance and maintenance can be done without too much trouble and without too much expense. All right, so that's all I had to talk to you guys about today, and I just wanted to kind of summarize the main takeaways for me. So small scale psychrophilic anaerobic digestion, technically it should be possible, but we need to build systems that are resilient, that have low maintenance needs, and where you have community buy-in to the system so that it gets operated well, and so that there are people in the community that are able to and willing to fix it and to work with it. So that's a lot of improvements that we need to make on the digester design side. And maybe also some simplified operational instructions and things that we can think about how to share this information with people better. Implementing psychrophilic anaerobic digestion doesn't solve all the problems that these people in these remote communities face in terms of avoiding human contact with waste, avoiding odors in the home, that kind of thing. That's another problem that still needs to be solved. And there are people working on that, but there's a lot of challenges. Using pilot digesters could enhance engagement with the community and reduce hesitation and really hopefully develop these champions that want to support these kinds of systems. And lastly, this cold high anaerobic digestion group is really awesome. If you're interested in psychrophilic AD and in WASH, you might consider joining. We are always looking for new people with new insights to join the group. And so I'd just like to acknowledge all the people that are members of that group, especially the people listed here. So Margaret McCauley, she's from the US EPA and she started this group. And she provided some of the information for the slides. Also, I mentioned before, Simone Saballo, she provided a lot of the kind of informational stats and stuff and a lot of the images that I showed today. Jasmine Perea has shared a lot of information with me about her anaerobic digestion system, and I just thought it was so fun and so exciting how passionate she is about this kind of technology. Angie Bywater is the one who runs the backyard garden digester. She provided a lot of information and pictures on that. And then, of course, Robin Schmidt, who actually made it possible for us to all finally meet in person by writing this grant to NATO that funded this conference. So if you're interested in joining Chad, this is where our website is. That gives information about the Zoom links for the meetings, the schedules, all that. So go to anaerobic collaborations, and then if you find teams, you'll want to find the cold high anaerobic digestion team, and then find our website through there. And that's it for me. So thank you for listening, and I'm happy to take any questions.